So the next chemical property, two more chemical properties are the oxidation and cyclic polymerization. Okay. So the next, oxidation. Okay. Like your alkene, here also the oxidation by strong oxidizing agent and ozonolysis. Okay. So the first one, strong oxidation, and you know the very same reagents acidified K2Cr to 7, alkaline KMnO4, hot alkaline KMnO4, hot acidic KMnO4, the very same reagent here also. Then you have to know 2 points. A terminal triple bond. Here all triple bond cleave to become acid. That is the idea. Okay. If the triple bond is in a terminal position, then there will be arrangement like this, right? C triple bond H. And this on oxidation with the strong oxidizing agent become formic acid. It become formic acid. What is this one? Okay, become formic acid. Ready? And you know this is a strong oxidizing agent. Your formic acid readily turns to carbon dioxide and H2O. Okay. There are two chances for different configuration. There are two possibilities for the configuration of double bond. Either a double bond without hydrogen or a hydrogen. For a triple bond with the hydrogen, it should be in a terminal position. So this cleaved to become formic acid. This become a formic acid. Okay. Else it turns to acid. Otherwise it turns to acid. Okay. I'll give you an example. Listen. If I have propine, which on treatment with the hot acidified KMnO4. What about the products? This triple bond cleaved and this become acid of 2 carbon, right? So CH3, COH plus this become formic acid and the final will be CO2 plus H2O. Okay? Fine. If this is your compound, John strong oxidation. No problem. This is cleaved, this also cleaved. Okay? So this become acid. How much carbon? 1, 2, 3, 4. So acid. Up to here. And the second one is CH3. COH. Okay? So all become acid here. Ready? You simply cleave the bond and make the all into acid. Where if in a terminal triple bond it becomes formic acid, it further turns to CO2 and H2O. That's only change. Okay? Show that. But in your alkene, there is a chance for the formation of ketone also. Okay? Without hydrogen, it becomes ketone. Here all become acid. Next, ozonolysis. Ozonolysis. Okay, like your alkene, here also two possibility, reductive and oxidative ozonolysis. Then what is the change means? Listen, here we have triple bond. Okay, in case of a reductive ozonolysis, a double bond may break to form a dicarbonyl compound. Listen, if I have RC triple bond, C R dash. Okay, let this be an alkyne which on treatment with the ozone. The forms an ozone ion. Ozone ion R C. You simply leave two bonds or remove two bonds. Okay, so that you can make a ozonoid like this. Okay, ready. Followed by the reduction or followed by reductive or oxidative ozonolysis. It become if it is a reductive ozonolysis, reaction is O3 in DMS. Okay, your product will be R C double bond O single bond C double bond O R dash. Like your alkene, you simply cleave the two bonds, add two oxygen. Ready? This is exactly we did in alkene. Okay, so you obtain a dicarbonyl compound. If this process an oxidative ozonolysis, first the forms a compound like this, very same compound, and most of reference book mentioned that it further oxidized or further cleaved here to become acid. Okay, so OH plus R dash CO, which means you simply cleave this and make it as acid. Cleave this all bond and make it as acid. Okay, most of reference books are giving like this. So I'll give you example. If I have propane, reductive ozonolysis, what happens? Cleave the two bonds and make oxygen. CH3, C double bond O, single bond, C double bond O, H. Pyrovaldehyde, methyl glyoxal. Okay, ready? Everybody know oxidative ozonolysis. Oxidative O3 in H2O, oxidative ozonolysis. Cleave this and make it an acid. CH3 COH plus HCOH. The further oxidation of HCOH is not usually taking place in presence of ozone. Okay, but in presence of strong oxidizing agent, this becomes CO2 and H2O. Okay. In case of reductive ozonolysis, you remove 2 bonds and make 2 oxygen. Ready? In case of oxidative ozonolysis, you completely break the whole 3 bonds and make it an acid. Okay. And this will be the intermediate oxonide. Okay. If we have alkene, we simply replace it by this connection. If you have an alkyne, you can replace the 2 bonds, but still there is a bond. Okay, and make an ozonide connection. That's a change. Okay. Fine. That's all about oxidation, or the last chemical property of your alkyne. Polymerization. 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 Okay. There are 2 types of polymerization in your textbook. That is linear polymerization. Linear polymerization means if I have n molecule of acetylene, you know acetylene is ethane, which undergoes polymerization in presence of radical coordinates. Leave one bond, so that's CH double bond, CH. You know the polymer structure. Okay. This become poly acetylene. This is the linear polymerization. Not much important. Okay. You are familiar with the polymerization of ethene. Okay. Where this bond is left to become something like this, like that. Here we have 3 bonds. You simply cleave a single bond to make a double bond. Okay. So this is linear polymerization. The next is important, cyclic polymerization. Cyclic polymerization. Cyclic polymerization. Okay. Cyclic polymerization, which is usually taking place in a red hot iron tube. Red hot iron tube, which means Fe in nearly 600 degrees Celsius, right 73 Kelvin. Okay, the reagent is red hot iron tube. Okay, this reaction has a specific idea. Listen, if I have 3 molecule of acetylene or ethane, ready, which passed through red hot iron tube, it undergoes cyclic polymerization to form benzene. So this can be treated as a method of preparation of benzene also. Okay, listen. It becomes benzene by means of cyclic polymerization. Okay, these are the 3 molecules of what? Acetylene, which are passing through the red hot iron tube. This undergoes a cyclic polymerization like this. This bond shifted to here to get a single bond. This to here have a single bond. This to here have a single bond. So here will be double bond, single bond, double bond, single bond, double bond, single bond, with all carbon having carbon and one carbon and hydrogen. Form benzene. Ready. So this example is given in your textbook. We can have more. If I have two equivalent acetylene and one equivalent propyne, it's passed through red hot iron tube. Okay, what happened means, listen. So let me show ethane like this. This is ethane. Here we have CH, and propyne like this. Okay. Ready? CH, C, CH. Ready? So this is ethane. We have 2 molecules of ethane with a single molecule of propyne. Is it okay? Fine. It's on cyclic polymerization. Okay. What do you take? Tell me. Agreed? So let this be the, it become double bond. Here will be a single bond. Here it will be a double bond. Here we have CH3, then a single bond. Double bond. Totally ready. If I have one equivalent ethane and 2 equivalent propine. You know what happens? We obtain ortho, meta, para, silenes. You have 3 possibilities. Listen. Only 1 equivalent. Either 3 equivalent propine. Okay. This is the first chance. Second chance. The methyl group in propyl may be here. Propine may be here. It may be here or here also. But this is still here. Second chance. The third chance is methyl in propyl here. Here. Okay. Okay, fine, no problem. This become double bond, single bond, CH3, double bond, single bond, here is a CH3. Agree? Is it okay? Meta silane. Okay? Okay? Here it will be orthosilane, will be parasilane. Okay? Check it.
ഹലോ ഞാൻ ഒന്ന് വൈകുന്നേരം
രാത്രിയാവും എന്ത് അക്കൗണ്ടിലോ വൈകുന്നേരം മാത്രം വൈകുന്നേരം വരുമ്പോൾ വന്നാൽ മതിയോ ആയിക്കോട്ടെ ഉണ്ടോ മറ്റേ വൈകുന്നേരം വരുമ്പോൾ വന്നാൽ മതിയോ
ബാഗിലുണ്ട്. So chances will be more. There may be a chance for mesically. Okay. One chance will be for the mesically. Okay. Keep it in mind. Mesically. 135 trimethyl benzene is said to be mesically. Okay. More than one chance is there, but one chance will be mesically. Okay. So your alkane is over. I'll give you some questions. This is a cycloalkene. Ready? This is cycloalkene. Cis with respect to unsaturation in ring up to 8 carbon, cis only possible. So this is some kind of cis. So bromination. Bromination is a cis addition or trans addition. Trans addition. Okay. So there is a symmetric addition come trans addition. 2 bromines are added and there will be a trans pattern. Okay. Ready? I'm sorry. Correct. Cis to trans fine. HBr, Marconi co-addition. Right. Which one is the carbon with the lesser number of hydrogen? Here there is no hydrogen, right? 1, 2, 3, 4 valency means no. Here we have 1 hydrogen. Okay. So the negative part goes to here. And the hydrogen will be here, right? Okay. Next, HBr in H2O2, which follows anti-Marconi co-addition, where the hydrogen will be here and bromine will be here. Okay. HCl in H2O2, no. HBr in peroxide can show anti-Marconi co-addition. Okay. Normal HCl and HCl in peroxide, always the mechanism is Marconi co. Okay. So chlorine will be here, hydrogen will be here. Okay. Only HBr in H2 peroxide. This is simply KMnO4 in OH minus, and this is hot alkaline KMnO4. These two are entirely different. Now base reagent, right? Base reagent is a cis addition, and your molecule is a cis1, and the OH they arranged in a cis pattern, because cis plus cis will be cis. The next is hot alkaline KMnO4. There are 3 conditions. Terminal double bond becomes CO2 plus H2O. Okay, double bond without hydrogen, this without hydrogen become ketone. With this with hydrogen become acid. The bond cleave, this is a double bond without hydrogen, that become ketone. Okay, this is with hydrogen, that become acid. Ready? Diluted states of addition of H2O, acidic hydration, right, which follows Marconi co-addition. The next is reductive ozonolysis. So double bond without hydrogen become ketone, with hydrogen become aldehyde, not acid. Okay, if that is oxidative ozonolysis, double bond without hydrogen become acid. Okay. These are the reaction of alkyne. Cyclic alkyne is rare. Rare means because it is highly unstable. In your cycle, if there is a triple bond, what will be the hybridization? The hybridization of triple bond carbon is sp, right? If that triple bond which exists in a ring, what happens? The ring becomes sp. The ring becomes sp means ring have high angular strain, because ring can't exist as linear. So there is a chance for triple bond in ring is very rare. Okay, but double bond, okay, perfect, planar. So usually the triple bond will be in a open chain molecule, a cyclic molecule. So this is addition of dibromine, and you obtain tetrahalide, right? Tetrahalide. The next is addition of base reagent. Okay, and you know OH, right? OH. Followed by the condensation, right? Here will be an aldehyde, here will be a ketone. Agreed? Okay, 2 OH in carbon become carbon ion. Next is hot acidified KMnO4, okay, which is discussed from today. It
cleave like this, and this is a terminal end, become CO2 plus H2O, and the another will be a carbon of acid of 4 carbon, 1, 2, 3, 4, right? Okay. The next is reductive ozonolysis. What happens? You leave the 2 bonds, supply the oxygens. Okay. Ready. Reductive ozonolysis. The next is HBr excess. Repeated Marconi co-addition to form geminal dihalide. Okay. Ready? Benzene. That's all. Benzene. Okay, write some points. Molecular formula MF C6H6 C6H6 aromatic with 6 pi electrons, aromatic with the 6 pi electrons. Next, all carbon have bond order of 1.5, 1.5. All carbons have bond order of 1.5, not 2 or 1, it is 1.5 by means of its resonance, okay? 1.5. Next, bond length. Bond length 1.39 angstrom. 1.39 angstrom. Resonance energy 36 kilocalorie per mole. 36 kilocalorie per mole. Next, isolated by Michael Faraday. Isolated by Michael Faraday. Next, cyclic structure. Cyclic structure proposed by Kekulé. Okay. Also known as phene, P-H-E-N-E, phene. That's why we are using phenyl. Methane, ethyl, like that, phenyl. Okay, phene. Now, resonance energy means the energy difference between the resonance hybrid and canonical structure. I think you know that. Resonance hybrid and canonical structure. You know the hybrid structure of benzene. Okay, and you know the canonical structure, alternate bond structure. Okay. Next, preparation. Preparation. Preparation number 1. Aromatization of hexane. Aromatization of hexane. We already discussed it, okay. Aromatization of hexane. We know that cyclization followed by dehydrogenation, aromatization. We have normal hexane, which on treatment with the Cr2O3, Al2O3. Okay, which undergoes cyclic polymerization to form benzene, first one. Benzene is a typical molecule, okay. So one possibilities are there, only one possibilities from a typical compound. Because you have to prepare a single compound, not a generalized class. Okay, so one example should be there. Okay, if you have normal hexane, then only you obtain benzene. So the second, dehydrogenation of cycloalkene, dehydrogenation of cyclohexene, dehydrogenation of cyclohexene. You have a cyclohexene like this, okay, which can be dehydrogenated in presence of platinum. Platinum followed by heating nearly a sine of T Kelvin. So it dehydrogenated from here, okay, benzene, okay, dehydrogenation of cyclohexene, Next, cyclic polymerization of acetylene. Okay, cyclic polymerization of acetylene. So you have acetylene molecule. Ready? Which on cyclic polymerization? We already discussed data and you. Okay. We discussed the maximum possibility of that. Obtain benzene. Okay. Next, decarboxylation of sodium benzoate. Decarboxylation of sodium benzoate. So this is your sodium benzoate, which on decarboxylation with the soda lime. Okay, we already did decarboxylation of alkene. Hydrogen, and you obtain benzene. reaction is said to be deamination. From benzene diazonium chloride. You are familiar with the diazonium salt, benzene diazonium chloride, like this. Okay, if this on treatment with the ethanol, CH3, CH2, OH, or this on treatment with the H3PO2, phosphinic acid, hypophosphorus acid or phosphinic acid. What happened means the N2Cl replaced by hydrogen. N2Cl replaced by hydrogen, where the ethanol oxidized to ethanol, H3PO2 oxidized to 3PO. Benzene sulfonic acid. From benzene sulfonic acid. Okay. Ready. So this is your benzene sulfonic acid, which on treatment with the hot water. Or SO3 is replaced by H. Okay. Reduction of phenol. Reduction of phenol. So this is your phenol. Phenol on treatment with the zinc dust. Okay. So deoxygenation take place to become H. Okay, enough. Ready. These are the main preparation of benzene. No more other possibility because benzene is a typical compound, not a general class. Okay. Chemical property. Okay, first one, addition reaction. Addition. Addition reaction. You have benzene. Okay, which undergoes addition reaction. In presence of hydrogen in nickel. So all bonds are hydrogenated to form. It becomes a saturated compound, cyclo. Here we have C6, H6, bond cleaved, hydrogen, hydrogen, cleaved, hydrogen, hydrogen. All the unsaturation become saturated to form cyclohexane of C6, H12. Okay, or if the reaction is in chlorine sunlight, there may be a chance for addition. Okay, or all unsaturation attacked by chlorine. this? No. Benzene hexachloride. Benzene hexa, or abbreviated as BHC. BHC. Or it is also known as 666. What is the formula? C6H6Cl6 666, or gamexane, or lindane. Okay, it's used as an insecticide. What is the actual IUPAC's name? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Hexa, chloro. No, this is cyclohexane. Okay, this is a common name. Since the molecule is derived from benzene, they named it as benzene hexachloride. But there is no benzene. Okay, fine. That's a derived name since the molecule is from benzene. Benzene on hexachlorination. That's why benzene hexachloride. Okay, but there is no unsaturation like benzene. Used as an insecticide, okay. So these are the main addition reaction. There may be chance for ozonolysis also. Okay, next ozonolysis. The most important reaction is electrophilic substitution. Okay. Before that, we can discuss ozonolysis. 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 Okay. So you simply treat it in something like a cyclohexatriene, a cyclic ring with 3 unsaturation. Ready? Okay. So you know how to make the ozonolysis, how to design the ozonolysis product of an alkene. Cleave the double bond and put ox in the. Ready? That's the only idea here also. Okay. So listen, if I have benzene, it's on ozonolysis. Let it be reductive ozonolysis. Okay. O3 Zn H2. There forms 3 molecule of glyoxal. 3 molecule of glyoxal. Listen, this bond cleave OO. So there is no connection like this. Okay. Now there is no connection because it is cleaved to form OO, and each corner have one hydrogen, right? Double bond with hydrogen become so OO. Okay. Now there is no connection like this, or like this. It is cleaved. So we have CH is here, CHO. This connection is cleaved, right? So we have CH here, it become CHO, single bond, CHO. There is no connection like this. CHO, CHO. No connection. CHO, CHO. So 3 mole of dioxide, okay? Ready. What about the intermediate ozonide? Listen. You know how to design an ozonide. If these all are the bonds, okay? What is the idea? Remove the whole double bond, right? And make an ozonide connection like this. Okay? This is a equivalent ozonide, so it will be benzene triozonide. Benzene triozonide. Okay. Your double bond which is replaced by an ozonide connection. In this molecule also. Okay. and 2 equivalent glyoxal. Okay, you should consider this in this pattern also. Okay, what is it? The position of unsaturation is alternate. Is there any change? Is there any change in here? Or the same product? Oh, is there any change or the same product? Glyoxal, methyl glyoxal, both are same. Okay, you should consider in this pattern also. You can't predict the bonds are here, maybe here also. Okay, there may be a change if the bond position is changed. There may be in some other cases. Let's have a discussion about here. Fine. One glyoxal, right? Two methyl glyoxal. What about if the bond is alternate? Is there any change? No. Is there any change? No. No change. Okay. But if it is, listen, if it is orthosilane, what happens? Orthosilane. What about the product? Methyl glyoxal. So 2 molecule of methyl plus 1 molecule of glyoxal, right? Or this have a possibility like this also, right? Okay. Then check if there are any change. Yes. Right? This is not methyl glyoxal or glyoxal. Right? This is dimethyl glyoxal. Agreed? Agreed? Fine. The two others are glyoxal. Okay. So the possibility may be different. So you have to consider this pattern also. Okay. It is easy to design the product, right? Okay. Simply clear the bond and put oxy. It is easy to design the product, no problem. But you have to consider the bond alternate fashion also. Okay. So give the example of orthosilane also. Chemical property is there, said to be electrophilic substitution, or the most important property of any ring, any phenyl ring. Okay. Here the all position of your benzene ring is identical. So the idea is that benzene have all 6 position identical pattern. So if a benzene ring which is treated with a, what happen means this hydrogen replaced by electrophile, so it's said to be electrophilic substitution. Let it be Se, like Sn, Se, electrophilic substitution. Okay, so general category. And you know that benzene for H is a group which is neither electron donating nor electron withdrawing. If the hydrogen is replaced by a group which can show plus R resonance or plus some resonance, what happen means comparison with benzene, extra electron density will be orthopara portion by means of its resonance. You know plus R resonance. Okay, so there will be a donation to the ring, so we can feel extra negative charge compared to benzene in orthopara position. If that very same H is replaced by a minus R group, okay, which withdraws electron density from ring, where the impact will be at electron deficiency orthopara position. So if you have an electrophile, ready? Electrophile may attach on more electron rich center, right? So your benzene, all the positions are identical. Okay, so all the positions are identical for your benzene. But in comparison with benzene, if a molecule with a plus R resonance, the electron richness is relatively higher in ortho and para position. So molecule with the plus R resonance, I think you are familiar with that, they are ortho para directly. Okay, if hydrogen is replaced by a plus R resonance group, then that group direct the electrophile into ortho para position, because the excess electron density is there in your ortho para position. Whereas if a group is a minus R group, which can't direct the electrophile into the ortho para position because there is already an electron deficiency. This is an electron deficient species. So relatively there is an electron. Here the benzene, right? This is benzene. All positions have same kind of electron density. If it replaced by a plus R group, always the resonance operates in ortho para position. The resonance, the donation of this group having an effect in ortho para, no effect in meta position. So this meta position have a electron density which is exactly same as that of benzene, right? Okay, this meta position have electron density which is exactly same as that of your benzene, because resonance have no effect in meta position. But in addition to in comparison with the meta position, here due to the resonance, excess electrons are in ortho para position. That's why electrophile are seeking the ortho para position. Okay, but here comparison with the benzene, the ortho para positions are electron deficient. So there is a electron density in your meta position. There is no effect of this minus R group in meta position, right? So still there is a electron density which exactly present in benzene. So your electrophile can attack meta position. Ready? I think you know the concept. Electrophilic substitution is a common reaction which observed in all kind of benzene rings, all kind of phenyl ring. Even in benzene or any group which is replaced by benzene, plus R or it become a, so there we can observe the electrophilic substitution. Okay, but the directive property may change because it is due to the resonance. So now we are discussing electrophilic substitution of benzene. These are the usual electrophilic substitutions: halogenation, nitration, sulfonation, Friedel-Crafts alkylation, Friedel-Crafts acylations. Usual common electrophilic substitution. So these all are reagents which can generate a particular electrophile. Okay, but that electrophile readily substitutes a hydrogen to form the product. Okay, you know the general reaction. Okay, if you are given with benzene and some kind of electrophiles are there, it can substitute the hydrogen. Okay, and the first one, the reaction is known as chlorination. The reaction is known as chlorination. Okay, well, the reagent is chlorine in a Lewis acid, chlorine in AlCl3, chlorine in FeCl3, like that. Okay, where the electrophile generated is Cl plus, chloronium ion. Okay, these reagents can produce an electrophile, okay, which can attack or which can shoot the hydrogen. Ready? So the electrophile generated is Cl plus and obtain chlorobenzene. The next is, the reaction is known as bromination. So simply bromine in presence of FeBr3. Okay, or bromine polar solvent. That's okay. So here the electrophile is Br plus, and the product will be a bromobenzene. Okay. The next is ICl in AlCl3, where I plus may be generated, or I2 in HiO3. There is no FeI3 like that. Okay. So HiO3, and this reaction is said to be iodination, where electrophile is I plus. So you may have iodobenzene. Okay, and Normally chlorination, brominations, iodinations are taking place, not formation. So these are said to be halogenation. Okay, halogenation generally. The next is a mixture of concentrated HNO3 plus concentrated H2SO4. I'll explain the mechanism of this reaction, which is given. Okay, now just the reaction. Okay, the mechanism will be explained. Well, this is a process said to be nitration, where the electrophile is NO2 plus nitronium ion. Listen, if the reaction is in a low temperature, nearly less than 50 degrees Celsius, you obtain nitrobenzene as the major product. But if the reaction is in a high temperature, the very same reaction which is in high temperature, which means greater than 50 degrees Celsius, or nearly 100 degrees, something like that. Okay, then there is a change. First there forms nitrobenzene, as usual nitrobenzene. But the formed nitrobenzene is a minus R group, right? NO2 is a minus R group. Okay, so there may be a chance if the temperature is greater than 50 degree or the reaction is in a high temperature, there will be a chance for repeated nitration. Repeated in low temperature, nitrobenzene. 50 degree or in a high temperature, then there is a chance for repeated nitration. Repeated nitration means first forms nitrobenzene, which is a minus R group, so that the next electrophile, next NO2 plus may be directed to the meta question. So the major product will be 1,3-dinitrobenzene. Okay, if the temperature is higher, the major product is meta-dinitrobenzene or 1,3-dinitrobenzene. Ready? Keep in your mind. The next is sulfonation. We can use either fuming sulfur trioxide or concentrated H2SO4. Okay, where the electrophile is SO3, not SO3 plus, not SO3H, SO3. That's a neutral species. Okay, electrophile is SO3, but once it replaces, it becomes SO3H. Okay, I'll explain the mechanism, then it will be okay. Electrophile is SO3, not SO3 plus or SO3H plus, like that. Electrophile is SO3. But once it substitutes the ring or the hydrogen, it becomes SO3H. Okay, I'll explain the mechanism, then you can realize why it is so. Okay, now this is RCl. R means alkyl. The alkyl chloride in presence of a Lewis acid. Okay, and this reaction is said to be Friedel-Crafts alkylation. Friedel-Crafts alkylation, and listen that here forms the electrophile as R plus. What the electrophile is at? R plus. R plus means carbon plus, which means carbocation, which means there may be a chance for rearrangement. Okay. So if the R plus substitutes the ring, what happens? You obtain alkyl benzene. Okay. Before substituting, if there is a chance for rearrangement, then it undergoes rearrangement. Only the substitution takes place. Okay. Because the formed one is carbocation. So rearrangement possible. Fine. This one also RCOCl in AlCl3, and this reaction is known as RCO. R is alkyl, RCO is acyl. RCO group is known as acyl. R, you know, alkyl. So if you are inserting R group, alkylation. RCO group, acylation. Okay. So this is said to be Friedel-Crafts acylation, where electrophile is RCO plus. RCO plus, but the positive charge in carbon, okay, not in oxygen. You know what is RCO. You know what is RCO. Okay, so the positive charge in carbon. Ready? So your product will be ring, which is attached by COR. The attachment is by means of carbon. Okay, and you obtain aromatic ketones. aromatic ketones. These are the common electrophilic substitutions. Okay, so you should know the name of reaction and electrophiles from the reagents. Okay. when RCl treated with AlCl3, AlCl3 is a Lewis acid which accept electron pair. Which accept electron pair means this completely taken by AlCl3, the Cl minus, so that it become AlCl4 minus, and here will be the plus. Okay, so if it is clear that this is an alkylation, you simply remove the Cl, then you can make a carbocation. If rearrangement, make the rearrangement. Okay. Okay, fine. Okay, fine. So that generates a carbocation, right? Agreed. What about the carbocation? CH3 plus. Is there any reaction? No, so it's a simple substitution to form toluene. Okay, the next, that is, see, what is this one? Ethyl chloride. So the carbocation generated is CH3. Is there any rearrangement? Yes or no? No. So ethyl benzene. Listen. What about here? What about the carbocation formed here? CH3, CH2, CH2 plus. Is there any hydrate shift? What happened? To become isopropyl carbocation. Enough. Ready. Then only the attack. Then only the substitution. Okay. So the reagent is N-propyl chloride, but the molecule is isopropyl benzene. Is it okay? Okay. The molecule is cumene. Okay. But the addition is N-propyl chloride. Here also, this is the category, right? Okay, is there any rearrangement by means of hydrate shift? So you obtain third butyl carbocation, so that product will be like this, third butyl benzene. Listen here, listen. What about here? This is the uniformed carbocation. Is there any rearrangement? What kind of rearrangement? Third pentyl. Okay, third pentyl benzene will be the. Ready? This is this one. Yes or no? Yes. Where then, if the bond is formed, then either. Okay, what's the problem? That's okay. Ready? Wait, one more. This one. The forms a carbocation, but from the molecule itself. 1, 2, 3, 4. 1, 2, 3, 4, 5. It's a carbocation. Agreed. Is there any rearrangement? Yes or no? This is a primary. So rearrangement from here. It become secondary. Okay? Ready? This much is rearranged, right? Now what happens? Then the removal of hydrogen. Then you have to substitute one hydrogen, right? Agreed. Any hydrogen here or here. This is substituted by the carbocation, which means okay, fine. Then the product will be, let me 1, 2, 3, 4, okay. Ready? So that there is a bond from 3 to here. So 1, 2, 1, 2, 3. 3 can form a bond here. 3 can form a bond here. Ready? This is the bond. Here will be a methyl. Right. In your 3 there is a methyl group, right? Okay. All 3 makes a bond here. It will be like this. You know that double bond in presence of H plus that generates a carbocation. Mechanism of electrophilic addition. Right. This bond polarized to here. Okay. So here also they forms a carbocation where rearrangement is not required. Agreed. So here also a chance for. There is any carbocation along with the benzene. There is a chance for substitution. So here also isopropyl benzene formed. Ready? Sure. The H plus usually HF4 H3PO4. Show that. What about the next? This is a question that you have to discuss in your handout. Okay? A previously asked question. I think this question is in your handout also. HF means H plus. What happens? This bond polarized to anywhere, both are same. So this become minus and here will be plus. H plus attacked here. Okay, this bond polarized here, minus plus and H plus attacked here. What happens? It forms a carbocation. Now it becomes a single bond, right? But here will be a opposite charge. There is no more rearrangement. The benzene to form cyclohexyl benzene, right? This will be the product. Okay, because this make a bond with the ring. Okay, that bond is this one. Okay. India. Cleavage less substituted side. Usually the cleavage towards the terminal end, right? Which means less substituted side. If the bond if the bond shifted to left substituted side, so that we obtain a positive charge in more substituted position, right? The electron polarized to the less substituted side means they become minus, and more substituted side will be got a more stable carbocation relatively. So like that, if there is a methyl group, you simply polarize to the side where there is no methyl group. Substituted side, there is a methyl group means minus, so become tertiary. Okay, so always shift the bond to the bond towards less substituted. Double bond with the less carbon branches.
Less substituted side we get a positive charge.
No, we shift the bond towards left substitute side.
Negative charge.
Yeah.
Methyl get a positive charge.
If you have, this is your doubt. Okay, this is a more substituted carbon. This is a less substituted carbon. Usually, what we are doing, this is a less substituted carbon. This is a more substituted. So usually the polarization towards right. Exactly same. The polarization to the here. Less substituted side. So that here become minus, here become plus. So you obtain a more stable carbocation. Okay. What about here? What about the carbocation? Minus H plus become opposite side. Agreed. Which undergoes a cyclization. Okay. Like this. Is it okay? 1, 2, 3, 4, 5. 5 carbons are there. 1, 2, 3, 4, 5. So 4 is attached to the 4 can replace this hydrogen. One, two, three, 4. 4 can make the bond. Or 4 have a methyl group. Okay. The next one. Actually, we know that if we have CH3COCl here, some kind of acylation. CH3COCl. If you have a CH3COCl here, what happens? We have AlCl3 along with the CH3COCl. This is acylation, where the electrophile is CH3CO plus. So you obtain acetophenone. Agreed. Acetophenone. Like your acetyl chloride, this is said to be acetyl RCOCl, acyl group. RCO group is acyl. RCOCl means acyl chloride. Acyl, if the R is CH3, then it is said to be acetyl. RCO, acyl. CH3CO, acetyl. R, alkyl. If R is CH3, methyl, like that. R is CH3. Then CH3CO will said to be acetyl group. Generally the category known as acyl. All RCOs are known as acyl generally. If the R is methyl, then it is acetyl. If the R is hydrogen, then it is formyl chloride, HCOCl. Okay, HCOCl is unstable. HCOCl is actually unstable. So we can't take a HCOCl in an isolated form. Okay, we can prepare it in a instantaneous pattern. So for the preparation of HCOCl, we used HCl and CO. Okay, ready. So this can impart an effect of what? This can produce an effect of what we isolate HCOCl because HCOCl is unstable, formyl chloride. So if a mixture of carbon monoxide and hydrogen chloride is used, what happens? It behaves like an HCOCl to form benzaldehyde. The very same substitution reaction. And you know this reaction is known as Gattermann-Koch reaction, which is given in your aldehydes. Okay? Show that. This is wrong. LCl3. LCl3 can abstract the Cl minus, right? So you remove the Cl minus so that you obtain a carbocation. Okay. So that will be your product. Cl, benzoyl chloride. Okay. Wait. If benzene excess, if the benzene is excess, which means first you form what? Benzyl chloride. The very same reaction if the benzene is excess and along there is moreover there is an AlCl3, what happens? In the first substitution you obtain COCl, that's okay, because carbonyl chloride COCl2 is given or Cl minus abstracted by AlCl3 to become formyl chloride ion, which is substituted to form benzyl chloride. Okay. In the reaction, if benzene is excess, there is a chance for the next step. That is in presence of AlCl3. This Cl minus replaced. Okay. To become benzylonium ion, which can substitute the benzene to form benzophenone. If and only if benzene is excess. Okay. Like that here also. What about the case here? Normally what is the electrophile? CH2Cl plus. Agreed. CH2Cl plus. So here will be CH2Cl. If your benzene is excess, what happens? This Cl minus replaced to become benzyl carbocation, which forms diphenyl methane. Okay? Ready? These are extended examples. First you have to know normal case, okay, like halogenation, nitration. Ready? And the rearrangement possibility for Rayleigh-Craft alkylation. Okay. These all are extra examples. First you should be well familiar in the normal reactions. Then only you can practice this.